Hello, my name is Molly Smallcomb. I'm a PhD candidate at Penn State studying acoustics, and my project today talks about the histological examination of focus ultrasound disruption of ex vivo tendons. Our motivation behind this project is treating tendon injuries because they're common and costly to our society. They account for 45% of the 66 million musculoskeletal injuries occurring each year and can cost up to $114 billion. There are conservative therapies out there and try to relieve pain and restore mechanical function by creating some sort of microdamage to induce this healing response to the degenerated tendons, but they all produce mixed success. This brings us to our idea of using focused ultrasound therapy, which can create different bioeffects within a small focal volume, but the one we're interested in is a mechanically induced disruption. What happens is if you create and oscillate and collapse microbubbles in the focal volume, you can introduce a mechanical disruption at the target tissue within this volume. Though where my research comes into play is that collagenous tissues like tendon have been resistant to this type of focus ultrasound disruption. In preliminary data, we applied conventional Boiling-Kostrupski parameters to ex vivo rat tendons, but that produced focal coagulative necrosis. So that would be more in the thermal mechanism realm than the anticipated mechanical disruption. Though we did see successful creation of bubbles, as indicated in our ultrasound B-mode imaging as this hyperechoic activity within the tendon. Though looking at an H&E stain in the center and the NADH stain, we see these clumping of fibers, denatured proteins, and a thermal type cell death. So this brings us to our motivation to expand on these parameters and identify the acoustic parameters needed to introduce this controllable mechanical microdamage in tendon. For our experiments, we used ex vivo Achilles tendons and supraspinatus tendons from Sprague Dawley rats and aligned them and treated them with focused transducer in a water tank, and then monitored and aligned it with ultrasound imaging coaxially. So we applied 6 different sets of parameters, all varying in peak positive and negative pressures, or changing the pulse duration, or changing the treatment time. And then from there collected our samples and histologically analyzed them using a scoring rubric. So from this table, 2 or greater would indicate that there was focus ultrasound induced damage, but a score of 4 would indicate that we're now getting into the thermal realm rather than wanting that mechanical disruption. So here are some key findings from my results. We saw that decreasing our pulse duration led to more mechanical rather than thermal injury. So for example, in our set 1, which had short, quick pulses at 1 millisecond duration, we had 2 samples displaying thermal injury, while 3 displayed the mechanical injury. We also saw this trend with even shorter and quicker pulses of now 0.1 milliseconds in set 2, with none of them displaying thermal injury, but 4 samples still showing mechanical type disruption. So here's an example of a score of 2 in these images where we see this localized separation of the fibers, but no coagulative necrosis or distinct cell death of the nuclei. We also saw a trend that when we decreased our treatment time, that also led to mechanical effects over thermal injury. So with our shorter treatment time, but still a 10 millisecond pulse, we saw none showing thermal type effects, but we saw 6 showing a mechanical type disruption. So here's an example from one of those samples showing that there's a localized fiber disruption in the H&E stain on the left, but on the right in the NADH stain, there's no type of cell death, which would be indicative of thermal injury. So when we increase that time by keeping other parameters constant, so right before we were at 15 seconds, now this set 5 is showing 30 seconds. That increased time led to 3 samples showing thermal type injury, this coagulative necrosis, and distinct cell death. If you would like to know more details or see where our work is heading, I'd recommend checking out my poster or reaching out for further questions. Thank you to my collaborators, and this work was supported by the NSF GRFP and an NIH grant. Thank you all for your attention.